Recently, I had an idea about testing how long a car turn signal bulb lasts. How long would one of these bulbs last in terms of how many flashes before it burns out? And I know a way I can test it by using one of these Raspberry Pi single board computers. I need to design a system that can flash one of these car turn signal bulbs at the exact same rate that the car does. Each time the bulb turns on and off, I'll need to count that. Also, I will need to turn off the system and save that counted number when the bulb burns out. This way, you can keep track of how long one of these bulbs lasts. I'm testing this because I've seen numbers online for the lifespan of these bulbs of about 4,000 hours. However, I don't know if that number is for continuous use like a normal light source, or for flashing use in an indicator. And to turn on and off the bulb, I will use one of these MOSFETs. But before I wire this, I'll show you the circuit that I'll build. Here's the plan. The circuit involves an incandescent light bulb connected in series with the N-channel MOSFET. The MOSFET gate is connected to the Raspberry Pi's GPIO pin through a resistor. Also connected to the MOSFET gate is a resistor going to the ground so that the MOSFET turns off when the GPIO pin turns off, ensuring the lamp behaves as expected. The lamp is powered by a 13.5 volt power supply to simulate what is used inside of a car. And of course the Raspberry Pi will get its own 5 volt power supply from a USB charger. So let's build the circuit. For the pull down to ground resistor, I will use this 120 kilo ohm resistor, and for the series with the gate resistor I will use this 330 ohm resistor. I'll put the circuit together on this breadboard. The left pin of the MOSFET is the gate. This over there. The source pin of the MOSFET, which is the far right one, will connect to the power supply ground. The drain will connect to the negative of the lamp. I already have wires soldered to the Raspberry Pi, so I'll just plug this one into the MOSFET gate resistor, and this one into ground. These wires are soldered to the correct pin in reference to the pin out diagram that I will put on screen and linked in the description. And for testing, I'm going to use this old 12 volt, 12 watt bulb from an unknown source. And for my power source, I'm going to use a voltage booster connected to the 12 volt output of a computer power supply. Negative wire, just plug into the negative terminal with the breadboard. The positive wire, this will connect to one side of the lamp, like that. And the negative side of the lamp will connect to the drain terminal of the MOSFET, like this. Now everything is all wired up. When I turn on the switch, the boost converter should output a random voltage. So I'll disconnect this. Now I need to measure this and set it to 13.5 volts. And the output of the boost converter is 12.05 volts. And I will adjust it to 13.5 volts. Close enough. I'll connect the power so that the circuit is all connected. Now when I turn on this, the lamp should be off, which it is. Okay, so here's the program. I'm using the GPIO 0 library to allow me to control the output pin on the Raspberry Pi, and I have wrote some code to turn the lamp on and off every half second. Now, let's see if the code works. The lamp turns on for half a second and then off for half a second. Let me stop this with Control C, I think. And the lamp stays off, because I stopped the program when the lamp's off. However, all this does is just flashes the lamp. It doesn't keep track of how many times the lamp has been turned on and off. This stays on and off for a little bit longer than the time of the normal car's turn signal lamp. I should measure the car turn signal lamp somehow. I don't actually need to start the car if I use the hazard lights. And that's good enough, I think. So let's count the number of frames. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 frames. So we have 11 frames divided by 30 frames per second. So the lamp stays on for 0.36 seconds. Let's see how long it stays off for. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 frames. So a third of a second. Let's use 0.34 seconds. So the lamp needs to be on for 0.34 seconds and off for 0.34 seconds. I should probably plan the next circuit. For the next circuit, we need to be able to tell when the light bulb is burnt out. Using the properties of an incandescent light bulb, when the MOSFET is off, at this point here, we should measure 13.5 volts. So from this point, I will make a voltage divider, and at this point, we should get 3.3 volts when the lamp is off. We can connect the signal to another digital pin of the Pi so it knows when the light bulb is intact. Then, when the lamp burns out, we should see 0 volts when the MOSFET is off. To further protect the Pi in case I wire something wrong, I will use another resistor in series with the digital pin. I have determined that if I use a 6800 ohm resistor in the upper part and a 2200 ohm resistor in the lower part, we will get a 3.3 volt output. For the series resistor, I will just use a 1000 ohm resistor. So let's build this circuit. Now I will build the voltage divider circuit. I found a 6.8 kilo ohm resistor. The middle terminal of the MOSFET will be connected to the 6.8 kilo ohm resistor. And then the 2.2 kilo ohm resistor will connect from this pin to the ground bus, which is there. And there. So now I have connected my multimeter probes from the output of the voltage divider and ground to measure the voltage that the Raspberry Pi's GPIO pin would receive when this is working. I've modified my program from before that flashes the light bulb so that the lamp stays on 1.5 seconds and also stays off for 1.5 seconds. Now I will run this program. I'm going to turn on my voltage converter. We have 3.31 volts when the lamp is off, 0 volts when the lamp is on. This is behaving exactly as it should. Now I will wire the Raspberry Pi's GPIO pin to this point where the resistor is. And I will stop the program like that. So now it's time for a new program that will allow the Raspberry Pi to sense the voltage of the lamp and tell whether it is intact or not. Here's the new program. We are using the input device function from the GPIO 0 library. And I have set up the lamp. So the lamp sense, which I'm calling L-sense here, is connected to GPIO 22 of the Raspberry Pi with no pull-up resistor. And when the pin is pulled high to 3.3 volts, it'll output a 1. I have set up the code to turn on the lamp, wait for a quarter second, print the lamp sense value, wait for another quarter second, turn off the lamp, wait for another quarter second, print the lamp sense value, then wait again for a quarter second. This allows the circuit time to stabilize to ensure I am reading the correct value. Now, let's run this program. And now you can see that when the lamp is on, a 0 gets printed to the terminal, and when the lamp is off, a 1 gets printed to the terminal. And to simulate a burnt out light bulb, I will disconnect the positive wire here. And the terminal is showing all zeros. And I will connect this back, and you'll now see 1s appearing when the lamp is turned off by the circuit. So it's working as expected. Now all I need to do is add a way for this program to keep track of how many times it turns on and off the light bulb. Well, I spent a couple of days writing the program for this, and instead of using the incandescent light bulb, I'm now using a 16 ohm resistor and 12 volts LED strip. So here's the new program, and it's way longer than before, but this is because it has some very important functionality. This program will count the number of flashes and save it to a file And it will also keep a log file that gets updated every number of flashes defined by save interval, which currently is 10 for the testing I've been running. The delays also have been updated to match the timing of the car's turn signal. But now I will run this program. And it flashes much faster than before now and continuously counts up in the terminal. Now we'll stop this, and if we head back to the documents, we can see log file and save count. So if I open log file, you can see the log file keeps track of how many times the lamp flashed, and then if we look at the save count, it says 27. And if I start the program again, you can see that it starts back off from where we left off. You can see it was 27 flashes when I stopped the program earlier, and now it is counting up from there. This will allow me to do the test over multiple days, but code works good enough, I guess, so it's time for the big test. I set up the whole system underneath my workbench on a metal pan for safety, and let me run the code. And it still works, so I did not break anything. So I am ready to test with the car light bulbs. I modified one of the car light bulbs by bending its pins so I can connect alligator clips to it to connect it to the circuit. Now, after making the final touches to the code and figuring out a way of connecting the bulb to the circuit, it is now time to begin the experiment. I've set up everything needed for the experiment. I've set up the Raspberry Pi, the MOSFET circuit, the voltage converter, and the light bulb. I wrapped some electrical tape around the clips of this stand that holds the bulb so you don't create a short circuit with the metal stand. I have deleted the save count and the log file so that it's starting from scratch. Now I'm going to run the program, and this is either the moment of truth or failure. It is working exactly as designed. And it's counting up. Now, a little over an hour later, we have completed 5,740 cycles. It is now 11:22 a.m. on November 30th, and the light bulb is still flashing. And as you can see, we are up to almost 774,000 flashes. Also, I made a modification to the code, which changes the save interval from whatever it was before to 500 to prevent the log file from filling up way too fast. I'll make sure to post an update video when the light bulb burns out, so make sure to subscribe so you don't miss that video.